Thanks for coming out. I'm going to talk to you today about Amazon Lambda and what I think it's going to mean for the future of cloud. Lambda is really the first born in the cloud software architecture, and I think it's going to have a significant impact in the coming years on how people build cloud resident systems and also on the infrastructure that the cloud vendors use to deliver cloud. It's quite different from the first generation or the first model of cloud. The first model of cloud was based on virtual machines, and it was lift and shift. It was take your existing binaries, which run on a physical x86 server, drop them on a virtual x86 server, and you're off to the races. And that was great. It allowed the cloud to ramp very rapidly. But Lambda is really an inflection compared to that. And it's going to have some really big implications, I think. Now, that said, I don't think that the whole VM-based lift and shift approach is going to go away anytime soon, but I think Lambda is really the future. So what is a Lambda? A Lambda is a function or a method with a particular interface. And the interface is the same for all the languages, and it has two parameters. The first parameter is an event object, and the second one is a context object. And this method is activated by a particular event. And some examples of events, the arrival of a message on a REST interface. In Amazon's case, they have a service called API Gateway that will do that for you. And Microsoft has a very similar thing. A change in storage somewhere. So in Amazon's case, if you change a bucket in S3 or a table in Dynamo, you can launch a Lambda in response to that event. They have several queuing services, simple queuing service, simple email service, simple notification service. And in a message that arrives on any of those, you can light a Lambda in response to that. They have a service called Kinesis, which is a streaming service, very much like Kafka. So if you have a record that arrives there, or you can batch the records, you can invoke a Lambda in response to that. And Lambdas can invoke other Lambdas. So all the languages that are supported have an invoke method in the SDK, and so one Lambda can call another. And lastly, this is kind of interesting, I think, is CloudFormation is a service that Amazon uses, and Azure has very similar ones as well, that automatically constructs your services based on a JSON description. So you can actually have CloudFormation call a Lambda and ask it exactly what to build. And CloudWatch is their global monitoring service. So you can, all the services like EC2 and S3 and all these guys, they emit metrics into CloudWatch, and you can have a Lambda launch when any of those metrics crosses a certain threshold. And so all of these event sources here, they have their own custom event object, right? So the event object is specific to the event. So the context object is constant, and it's really mostly for the Lambda code to read it and ask it things like, what region am I running in? How much time do I have left? That kind of stuff. So how do you configure a Lambda? Number one is you don't deal with virtual machines, and that's why it's come to be called serverless in many cases. So you don't configure a virtual machine or instance. You don't bother with a full stack binary like you do with virtual machines. What you do is you just either enter or upload the source for your Lambda. You can use, the Lambda code can use most any standard Linux kernel call. You can fork a process, you can spawn a thread, call libraries that you want. If you have any esoteric libraries, then you need to include them in your upload package. Amazon has most of the common ones in most of the language ecosystems, but if you got anything more esoteric, you got to include that. You also then specify the trigger event that's going to launch this Lambda. You specify the maximum memory that's going to be used, that's allowed to be used by the Lambda, and you can specify a maximum execution time. Memory ranges anywhere from 128 meg to 3 gig in 64 meg increments. You can pick that when you configure it. And Amazon allocates CPU power proportional to memory size, which is just what they do with VMs as well. Oh, and the name Lambda, by the way, comes from the Lambda calculus. It's a mathematical formalism that's quite old, actually came up in the 30s, but it was kind of the basis for a lot of functional languages like Lisp. So when Lambda is executing, it gets access to environment variables. This is just key value pairs. and this is kind of standard, right, even in a regular environment. You can configure these at the configure time when you configure the Lambda, or you can have CloudFormation do it. There is a /temp directory that's available in the local file system. And very importantly, Lambdas are stateless. So when the Lambda stops executing, all memory resident state, global variables, everything, they're gone. And the /temp is going to be gone. So if you need to save anything, you have to write it to a persistent store. Oh, by the way, you guys can ask questions at any time. So there's two ways to, oh, I'm sorry.
You're going to post these slides later?
Sure. There's two ways to...
For the slides, if you can just post it and then put a link on the meetup page, there's a discussion section. And then everybody can just go to the meetup page for this talk.
Okay, cool. Two ways to invoke a Lambda, sync and async. With async, the invoker is not expecting a return, and with sync it is, so it'll block and wait for a return value. Most of those services, those event sources that I showed in the first slide, most of them are async, right? And they're hardwired. They're either one or the other. The only area where you get to pick the invocation type is in the invoke call. When a Lambda invokes another Lambda, there's a parameter you say, are you sync or async? Do you want to block or not block? So some of the constraints for Lambdas, these are the languages supported by Amazon. Microsoft has a subset. Of course, they have F# too. So JavaScript is actually, it's not just any JavaScript, it's going to be Node. Java, Python, Go, C# is most recent. This runs on Amazon Linux. You don't get to pick the OS. And I'm not sure about C#, so that might be different. But again, because you're not configuring a server, you're not dealing with servers, you're not dealing with an AMI, an image, a stack, the OS is just there, and it's Amazon Linux. The maximum execution time is 300 seconds, 5 minutes. Microsoft has it at 10 minutes right now. I'm pretty sure this is going to go up over time. By default, there's 1,000 concurrently executing Lambdas, and you can just ask Amazon and they'll increase it. And the reason they have these two constraints here is so that you don't shoot yourself in the pocketbook if you have an infinite loop and you light up 1 billion Lambdas and you get the bill at the end of the month. So these are just kind of bumpers to keep you from burning through your checking account. And the /temp directory is 512 meg. Now the other thing to know, yes?
Yeah, that's what I was going to ask, the startup time.
Right. So there's a cold start versus a warm start. I'm going to get into much more detail about this later. But right now, what you need to know is that if a Lambda has not been invoked for about, and they don't give you an exact number, but it feels like it's around 4-ish minutes, 4 or 5 minutes, then it'll take longer to start. And if it's less than that, it'll start much faster, and I'll get into why that is. All right, so let's take a look at a kind of a generic way to use Lambdas. So one of the common ones is you will have, say, a REST interface, a web server, some APIs that you're presenting to the world. In Amazon's case, they have a service called API Gateway, and you can have any number of endpoints. These are all URLs with particular HTTP methods coming off the public internet. And so there you can just assign Lambdas to these things. And when a message arrives, it'll light the appropriate Lambda, and whatever the Lambda returns, that's what it returns in the body. Lambdas can call Lambdas. And like I said earlier, Lambdas are stateless, so you're going to have to store some of this stuff in some persistent storage. Another common pattern is using the queuing services that they have. Lambdas or VMs can put messages into the queue, and Lambdas and VMs can pull them out. And another one is that anytime someone modifies these S3 or Dynamo, you can light a Lambda in response to that. And another interesting thing is I told you about CloudWatch, which is kind of the generic monitoring service for all the services on Amazon. And you can light a Lambda in response to some metric on some service crossing the threshold. Oh, and the other thing here is that it's not all or nothing. So it's not like you can only use all Lambdas or only use all VMs, right? You can mix and match, and I'll go into coming up on why you might want to pick one over the other. So how do you price Lambdas? The cost of Lambdas is two components. One is there's a cost for every time you invoke a Lambda. And the second part is just like a virtual machine, there's a cost for every second that you're running. And the cost to invoke has nothing to do with memory size. It costs just as much to invoke a small memory Lambda as a big one. The execution time, again, just like virtual machines, it scales linearly with memory. So the larger the memory, the more it's going to cost you per second. The actual numbers are 20 cents per 1 million invocations. You get a million free every month. And then you get this funky little number here, 16 microcents per gigabyte second. Now, it may seem like it's priced a little differently than virtual machines because this gigabyte second is a different set of units than you're used to, but it's actually the same. It's because they both scale linearly with memory, right? So a virtual machine with double the memory costs double the dollars per hour. And it's the same kind of thing with Lambdas, right? A Lambda with double the memory costs double the microcents per hour. And they just happen to glue those two together to keep this. But the pricing model is the same. And you get 400,000 free gigabyte seconds a month. So what that means is if you're running a bunch of high memory Lambdas, you get a smaller number of free seconds than if you're running a bunch of low memory Lambdas, right? And they measure execution time in 100 millisecond granularity on Lambdas because these things may not execute for very long. So you have your VM, and VMs will typically have threads. Threads are doing things. Sometimes they may be blocked or they may be suspended, sitting in a thread pool. There's a bunch of threads, right? And with Lambdas, it's similar. And so let's say, for example, we have a web server. And so the events coming in don't care whether your web server is VM-based or Lambda-based, right? So the event arrival is going to be the same. But with virtual machines, you're paying this entire time, whether you're doing anything useful or not, whether you're doing a little bit of work or a lot of work. And with Lambdas, you're just paying when you're actually doing work, right? Plus the cost to activate. And so what this means is there are certain situations where a VM is actually going to be cheaper, and other situations where Lambda is cheaper. I'll go into more of that. But simplistically, the more work you're doing in the VM, if you're keeping it really, really busy, the marginal cost of the piece of work is zero because you're just paying by the minute, no matter how much you're doing. Whereas in Lambda, it scales linearly with the amount of work, right? Now on performance, all these threads or closures, if you're running node, they're all competing for the same pool of CPU and memory. Whereas in the case of Lambda, each one gets its own dedicated slice of CPU and memory, right? So what that means is that as the event, more and more events are coming in, the Lambda performance per event will be fairly flat because each new event gets a dedicated chunk of CPU and memory. Whereas in the VM, they're all, more and more threads, for example, are being launched, and they're all competing for the same, 8 gigabytes, and they'll start to trail off in the performance per event. So that's something to consider. So the question was, are Lambdas, do they run to completion or can they be preempted? They will kill it after 300 seconds, right? That's the max. You can also set, at the time you configure a Lambda, you can configure a lower number and they'll stop it there. And I think they might stop it if you try to go over the memory limit too. So what I've done here is I've taken two instances, M4 and M5, and these are called general purpose instances. And Amazon states in their documentation that they scale the CPU capacity of a Lambda in the same ratio as a general purpose instance. So I took these two guys. And again, as I said earlier, the VMs, the cost of the VMs in dollars per hour scales linearly with memory. So you can convert that over to $1 per gigabyte second number and use that to compare with the Lambda number. So when you look at an M4 or M5, they're around, 4 times 10 to the minus 6, 4 microcents per hour, gigabyte second, whereas a Lambda is that 16 microcents, right? So what that means is Lambdas are 5 times more expensive, with time and memory. Now this does not include the free tier. So this is it'll be less than this because you'll subtract so many 400,000 gigabyte seconds off. Oh, by the way, Amazon has stated that that the free tier is permanent. This is not a temporary gimmick. It's going on. So when you let me go into more. I hope this slide is not too confusing. So the x-axis here is the average number of invocations per second over a month. The y-axis is the average length and execution time in milliseconds over that month, right? And so imagine there's a third axis coming out of the page, which is cost. So virtual machines do not care about activity. So the cost of a virtual machine is a flat plane, right? Whether you're doing anything or you're doing nothing, it's still 20 cents an hour. But the cost of a Lambda is a curved plane, right? So at the origin there, it's 0. If you're not doing anything, it doesn't cost you anything. And at the upper right-hand corner is the peak. The more you do, the more it costs. And it goes up on both the x and y axis, so it's like a hyperbolic curved plane, right? So these lines are where those two planes intersect, where they're equal in price. So to the lower left, at that level of activity, Lambdas are cheaper. A Lambda-based system is cheaper. On the upper right, at that level of activity, a VM-based system is going to be cheaper. And the 4 different lines are just 4 different memory comparisons, so they're kind of the same. So this kind of tells you what should have been obvious from looking at the numbers, is that if you have a very, very active system, it's probably better to do a VM. If it's not that active, do a Lambda. And again, like I said earlier, it's not all or nothing. You can modularize your system in some intelligent way, where you take the less frequent stuff, do it in Lambdas, do the more frequent stuff in VMs. So Lambda is not completely new. There is a paradigm, 2 paradigms called actors and communicating and sequential processes that were actually developed in the 70s for approaching a concurrency, right? And what they do is they have modules that execute in parallel. They have no shared state, and they communicate by passing messages. Like Erlang, for those of you who are familiar with that, that's an actor-based language. And so obviously Lambda is very heavily influenced by that paradigm. And then today you have microservices, which I think is really more of a new word than a new paradigm. You decompose a system into modules, like we always do with software. Typically they have a REST interface, HTTP based interface with some URL, and they're typically stateless, So that's very compatible with Lambdas, right? So really this whole thing about Lambdas and actors and microservices, they're all really points on the same spectrum. The big difference is how did you modularize and what is the communication between the modules? Now let's take a look at what this is for Amazon. I know a little bit less about Microsoft, but I know some of it. So each Lambda inside Amazon executes in its own container. It's not a Docker compatible container. It uses the same interfaces, the kernel interfaces that Docker uses, C groups and namespaces, but it's not Docker. This container is not visible to the user. You don't configure it. You don't have a Docker file, anything like that. It's built for you. These containers execute on a Linux, like I said earlier. Again, you don't get to pick. It's there. And multiple Lambdas can be running on a specific Linux, right? And that thing runs on a VM. All Lambdas that are on the same VM are from the same customer. So they never mix Lambdas from different customers on the same VM. And they do that for isolation, right? So evil people can't get access to other people's stuff. So you have your Lambdas, they're running away, and then it ends, right? And so what they do is they keep the container in memory for several minutes. And this is the difference between warm start and cold start. And if an event comes back within so many minutes, they just light the container. It's already there, it's on memory, and you go fast. Your code should never, ever assume a warm start. You can test for it. I've never done it, but I think you have to do it. They don't tell you in the context object, which I wish they would. But I think you can go and check like /temp and see if the stuff you wrote there is still there. But you should never, ever, you can't ever count on it, right? It's catch as catch can. So the problem with this, running this on VMs, and they ran it on VMs, I think for time to market reasons, they had EC2 already, and for isolation, there's a lot of infrastructure there rather than doing completely something from scratch and higher risk. So the problem with running on VMs is they take a long time to start up, and these things can take seconds, over 10 seconds, and a Lambda may only run for 200, 300 milliseconds, right? So you really can't take that hit. So what they do is they pre-build VMs. They have a pool of them sitting there, And they know it's all Linux, right? So they build the Linux container, and that's sitting there as well. I don't know this for sure, but I suspect they pre-build some containers by language. Like for Java, they'll preload the JVM. For JavaScript, they'll preload Node. And so they're just sitting there, and all they're waiting on is your code. So the event comes in, they stick your code in, and they launch the container. And this works most of the time. There are times when you might get ahead of their pre-building. But that's what they do to get around the fact that virtual machines are really not the best execution environment for Lambdas. So now some thoughts on yes?
So what, say it's a 3 gigabyte Lambda, how long does it both start?
Repeat the question for.
Yeah, so the question is for a 3 gigabyte Lambda, how long is the cold start? I don't think the cold start's a function of memory size. That's not exactly true. So what they say is that because CPU capacity scales with memory, if you have a larger memory Lambda, it should light up quicker because it has more time on the CPU. But for just start to finish, it's like seconds.
Seconds.
Yeah. I mean, in worst case, they have to build the container.
Like single seconds, like not 50 seconds?
No, I don't think it's tens.
Mentioned that even customer is on the Lambdas are on the same VM. So then what have you exactly said? You actually own the VM, right?
So the question was all Lambdas on the same VM from the same customer, yes. And so at some point the VM runs out of capacity and they have to light up another VM for that customer, right?
It will be again exclusive to that customer.
Yes.
So then what is the granularity here? It's still a VM, right?
Yes, it's a VM. And I don't know how much, well, they have to make some kind of guess about how much memory to give to the VM, right? And then they just allocate it to each Lambda as they light them. And at some point they run out. They have to either expand the memory for that VM or light another VM.
I was talking from the point of view of the customer.
Yeah.
They need a VM, right?
So
the Lambda thing is actually their business then.
the customer does not see the VM. They don't know that one is there, and they don't see the container. They don't know that that's there. All they see is there's a Linux API. So you cannot tell whether even the same Lambda, right? I light the same Lambda at different points in time. It may be on different VMs. So that's really the
Implementation is using VMs, but the customer only sees Lambda.
correct. So the question was the implementation is using VMs and it's using containers, but the customer doesn't see any of that. And that's one of the advantages of Lambda. That's why they call it serverless. Is you don't have to spend any time configuring anything. You just say, this is what I want to do, this is when I want to do it, send me the bill.
So if your Lambda needs only small amount of memory, then you will have to share the VM with many such Lambda instances.
So the question is, if the Lambda needs a small amount of memory, will more Lambdas be on the same VM? And yeah, probably. Yeah.
Isn't that unfair? If you have a computer that's down,
So as each Lambda gets its own slice of the CPU, which the VM has to own. So if you light 4 times more Lambdas, you're going to get 4 times more CPU capacity, right? It's allocated 1-to-1 to each Lambda. They're not competing for a common fixed number. And if, for example, in a world where they run out of memory on the VM or perhaps on the physical server, they'll just light up a VM on another server. But no matter where the Lambda runs on the same VM if these 2 Lambdas run on the same VM or if they run on separate VMs, they still get whatever the memory you configured them to get. And a proportional amount of CPU time. So that's what that performance graph I showed. Lambda performance should be approximately flat, right? You can light up 1 million of them, and they all get their own X amount of memory, whatever you configured, and their own X amount of CPU. So it should scale really well, right, relative to lighting up more and more threads on the same VM that's competing for a fixed pool of memory. All right, so Lambda, I think, is going to have a big impact on the cloud vendors' infrastructure in addition to how we all build our systems. And one of them that I think is interesting to look at is what I call transparent persistence. So accessing, because Lambdas are stateless, a common pattern is when you light up the Lambdas, you read something from a persistent store, you do some math, and then you write it back out, right? So, and the developer has to do this. So one thing I proposed actually to Amazon was to allow the developer to specify, I want these objects in that Lambda. So every time I start, I want to see them. And I don't want to have to waste my time having to read them, just make sure they're there. And so when you start, they auto restore them for you, and then when the Lambda finishes, they'll auto save them for you and guarantee that everything is there and it's all consistent without the developer having to worry about what am I doing with what database, et cetera, et cetera. And I'll talk later about the Lambda Graph, but you can, Lambdas, as you saw in that picture I had way back when, all cute little circles and boxes, it's like a graph, right? It has nodes and arcs. And so, Lambdas, like actors, can be expressed as a graph. And so knowledge of this graph can be used to prefetch these objects, right? If I can have a very high probability of knowing that Lambda X is going to go next, I can know what objects to have ready for them. And you can specify these things either statically or by configuration. And like I said, this takes some load off the developer. And actually, you're conveying your intent to the cloud vendor's infrastructure so they can do things for you. Because one of the things that Lambda does is in Cloud 1.0, you had this AMI, this big binary, and there was no way for the cloud vendor to look inside of it. They just said, well, there's a bunch of stuff, I'm going to execute it, I'll do what I'm told. With Lambda, you're now actually exposing to them some of the decomposition of your system, and so they can use that to do things for you and for them. And the access controls, et cetera. So the other interesting thing to look at is, well, spot Lambdas. We're all familiar with spot instances. So when you think about the cloud vendor's problem, the cloud vendors all went out and they bought 1 million servers. And they wrote a $1 billion check. And now that's sitting on their balance sheet. And they have to monetize that $1 billion as much as they possibly can, right? And they're buying more and more servers every unit time, right? So in this graph, the very top line is the number of servers. Let's just call it instances that they have. And the yellow region is the on-demand instances. It's like people are saying, I want this, I want it now, and I'm going to use it as long as I use it. And it's kind of a time-varying thing. And then that dark orange is, they always want to have a gap, right? You don't want to go all the way to the top of your physical availability because that means you may have lost revenue. They always want to stay ahead of what the usage is. And so that gap is why they created spot instances. A spot instance is you use it, it's an auction mechanism, and you can use it, and it may be taken away from you at any time. But without spot instances, all that orange area was not generating any revenue for them. But with spot, we all auction off, we bid on these things and we use it for as long as they allow us to use it. In my experience, spot prices are under half the cost of on-demand prices. And my last company, we used them for our test clusters. We rarely lost them. We would always bid half, and our test didn't run forever. But I don't remember us losing a spot instance very often. So that's why spot instances were created. It's an economic reason. Well, so there's a similar thing. They have a similar problem with Lambdas, right? It's not an instance anymore. It's Lambdas. And I got to fill all these things, all these slots on my physical machine with Lambdas because I, the cloud vendor, want to get revenue, right? I don't like machines sitting around not doing anything. So if you can develop a mechanism, the cloud vendor can do this, to allow the customer to say, you know what, when the event happens, you don't have to run the Lambda right now. You can run it at some point in the future. You could say something like within 30 minutes of it, or within an hour, or I need it by Friday at 5, that kind of thing. Or if you're doing dynamic pricing, if price falls below X, then it becomes worth it for me to run this Lambda. So with that flexibility, it gives the cloud vendor the flexibility to move the scheduling of the Lambdas around and fill all their empty slots. And what they can do is actually just what they do with spot instances is sell you Lambdas at cheaper, right? If you say, hey, here's a spot Lambda, Run it when you can. And, and you may have us say something like, well, if you can't get it done by Friday at 5, then do it now. Do it then for sure, and then charge me more. So I think that's an interesting thing to pursue. Yes? So the question was, Amazon will send a signal to a spot instance when it's about to be killed. I think they give about a 30-second notice. So the spot lambdas do not exist yet. This is
No, but Lambda in general. There's a limit, right?
yes, there's a 5-minute limit, and I don't know if they send a signal. There is a way in the context object, which is the second parameter of the Lambda, where you can call a method on it, and it'll tell you how much time you have left. But I don't think there's an interrupt or a Unix signal that says, hey, you're about to die. Not to my knowledge. Oh, so reserve instances, I didn't talk about this, but reserve instances are a form of future, like pork belly futures. These are people paying in advance for an instance. So what that means is, say you're a cloud vendor, you're Amazon, and you're thinking about, should I buy another 100,000 servers or another 200,000 servers? I don't know. So if people are giving you a signal here with reserve instances. If you have 50,000 reserve instance contracts, well, it's very low risk to buy those now because people are paying for it now. Or they're contractually on the hook to pay for it. You don't have to pay for all of it. But so reserve instances are a future signal on future demand for instances. So all of this, by the way, is taken right out of financial markets. There's spot markets in a lot of things. And similar, reserve instances are really instance futures, just like wheat futures. So that's why in this graph right here, it says it's lower risk. It's lower risk because people have already paid for it, or they've already signed a contract to pay for it.
But from a performance point of view, is there any?
No, reserve instances and spot instances are purely economic innovations. They're not technological innovations. There's no difference. I think one of the things that people may not realize is that cloud is really as much of an economic revolution as it is a technological revolution, right? Cloud converts what used to be fixed cost CapEx sitting in your data center that you had to carry on your balance sheet into variable cost OpEx, right? You only pay when you get revenue. So as I was saying earlier, you have a bunch of Lambdas, they're all running on some VM, but they're not just dissociated Lambdas, they're actually a graph. Lambdas are calling Lambdas could be calling other services. And so if you can convey knowledge of this graph into the infrastructure, then they can use that to some advantage. So right now, Linux, for example, is a thread-centric scheduler. Yeah, it could be a DAG. This is just this is poetic license, right? Yeah. It was easier for me to draw this than to have, it takes a long time to draw these pictures, man. So imagine an arbitrary graph here, right? So if we can convey a knowledge of the graph into the scheduler rather than scheduling threads, and it has no idea what thread depends on who, they're just threads, right? They have priorities, but the priorities don't change that much. It can actually schedule the graph. And so it can know ahead of time, there's a high probability if I execute Lambda A, I'm going to execute Lambda B. So I can prefetch it, I can get it ready, I can get rid of the cold start problem, things like that. And they can also do things like schedule Lambdas that talk to each other on the same physical machine and save network bandwidth inside their data center. Right? If two Lambdas are talking to each other and there are different physical machines, that's going to burn network bandwidth on their part. If they're on the same machine, they can talk via shared memory on that same machine. So there's a lot of things I think you can do to if you convey graph knowledge, and the graph isn't just Lambdas, it can include services as well. I know that this Lambda always calls SQS. So if you can also, if the cloud vendor's infrastructure can keep history and trace analysis, that can just add more information. The graph, at least from my experience with Erlang, most of the graph can be inferred by looking at the code. It's very clear. The Lambda A calls Lambda B. It's right there in the code.
So your guess how far Amazon is from Playmaker, something like that?
So when I showed them these everything since Prognostication 2.0, I showed this to the guys who created Lambda. I mean, they were smiling. I mean, they had me back. So I think they're thinking along. I don't know if they're thinking along those lines, but this was of interest, and I'm sure they're doing other stuff too, right? So I don't think you need to know the entire graph to get some advantage, right? If you know a lot of it, every arc that you know about the graph will help, right? You don't need to know 100% of them to get it. So as I said earlier, virtual machines are not actually needed with Lambda. With Cloud 1.0, you're selling time on a virtual machine. So by definition, you must have a virtual machine. You don't really need virtual machines with Lambda. And virtual machines, they consume MIPS and megabytes. They're complex. They take a long time to start up. But they also have isolation, right? So you need isolation between your Lambdas. So I don't know where it's going to go, but imagine a future where you can execute Lambdas in containers, and therefore you get isolation. You don't need virtual machines. And really, I think the question is, what's the attack surface? So in the case of a virtual machine, you get an entire binary stack from the user. And you must assume users are evil and are not intelligent and are buggy, right? So everything in that stack could do something bad. And so what the attack surface there is the hardware API, right? OSs hit registers in the CPU, they hit registers in the I/O silicon, which are virtual, but they're still hitting them. And so the cloud vendor has to protect against that. Whereas in the case of Lambda, the attack surface is the OS API, right? The cloud vendor provides the OS. The user only provides the app, quote unquote, above the OS. So the evil user can only try to attack the OS API and see if there's some way in. So those are two different attack surfaces. I don't know which one is easier to defend, but it's an interesting thing to consider. And when it comes to isolation, all isolation is based on the same silicon mechanisms. You have address spaces, you have page granular access controls, you have the VTX instructions that Intel and AMD put in. So whether it's a container or a VM or an OS, they all have access to that. So the other thing to note is that Lambda graphs are not just on, for a given customer, are not just going to be on a single virtual machine. They could be on a bunch of different virtual machines, and in fact on a bunch of different physical machines. And of course, they're hitting other services, right? Whatever it is, SQS, S3, you name it. So that means if you're going to schedule the graph, you're going to want these things to talk to each other, right? It's going to be a distributed scheduler. And the other thing I think is interesting, Microsoft does this in a way, is make the graph hierarchical. So a node in the graph is just another graph, right? And so I can use that as a component of sharing, of reuse, and also I think of accounting. Of being able to tell the user, this is how much that thing is spending. And Microsoft does this. They built their Azure functions. They don't use containers. They put it on a VM. They have it's like a Docker daemon, but they call it a Azure function daemon, and it runs on that. And they call it apps. It's because when Microsoft built their Azure functions, they reused service jobs, or web jobs, and service something. These are existing services that they had that would automatically light up new VMs, scale them up and down in proportion to load. So they use that very same thing on Azure functions, and it allows you to group a bunch of Azure functions together as a quote app. So the other thing that's, I think, interesting, and really the next shoe to drop, as I said earlier, cloud is as much an economic revolution as a technological revolution. And when you think about it, the customers who are buying cloud, they're spending their limited IT budget on some cloud services in order to get some value, right? So if you can develop a mechanism for the customer to say, this is what's important to me, this function over here or this path is more valuable to me than that one. Or this app maps over to my business process X that's more valuable than business process Y. That would allow them to quantify where their IT money is going and what they're getting for it. And effectively makes a business process a first-class citizen. And if you can use this, what I'm calling that app concept where you can encapsulate Lambdas, you can use that as an accounting kind of encapsulation. You can say, well, I have these I have this app, I have these two Lambdas, here's the cost the cost distribution that they're experiencing over some time. Here's the total cost breakdown for this entire app for the month, that kind of thing. And so I think initially you'll go to the business people and you say, you're spending twice as much to sell a DVD as a book. Does that make sense to you? And they say, well, no, because we make half the margin on DVDs and books, so something's something's out of whack. So why don't we rethink the design of our software? And then it's not just individual things. And by the way, Amazon Xray does this. They announced this. By the way, they announced it after I did the slide, just to be clear. So Amazon Xray is a really good start. And Amazon Xray does graph tracing or trace monitoring through your Lambdas. So it's not just about individual points, but it's also about paths. So I can say, here's my starting Lambda, here's my ending Lambda. This is some business process. Here's another business process. I want you to tell me anytime it starts to anytime it ends, where is my money going? And how much time am I spending? So this is kind of the idea that I believe that it makes the economics of the customer's business, the businesses that you guys work in, allows you to map the money you're spending on cloud to the money you're making in some business context, which I think is going to be really important. And that's all I have for today. Any other questions? So the question was, let's say you want to use Lambdas for a machine learning thing with GPUs. Right now, Amazon does not offer a GPU Lambda. It's just a general purpose. And the other point is, if you're doing, say, a machine learning or something like a simulation that needs to run for 30 minutes, Lambda is not the appropriate thing because there's a 5-minute limit on it. And even with Microsoft, it's a 10-minute limit. Now, right now, Google Cloud Functions is there. It's still in beta, so it's not really, they're still thinking about it. So I'm hoping that once that gets into the market, maybe Google will start some price competition. And because right now, when you saw on the earlier graph, Lambdas are 5 times higher in cost than, say, an M4, which is a general purpose instance. So I think there's some room to compete the price down. I'm hoping that comes down over time. And I'm pretty sure, I really expect that over time, they're going to increase the amount of time a Lambda can run. But if you're going to run something for 30 minutes, 60 minutes, Lambda is not the right answer today. So the question was, what are some interesting use cases? I've used it for a web server, REST interface, right? And it saved me a hell of a lot of money. There was an interesting use case I saw. It was some academic researchers did it. They took an S3, a bunch of S3 buckets, which have names, and they would write to them, not for data, it was like a namespace. And so they would actually write to a bucket name in S3, which would cause a Lambda to run, to do something, which would write to another bucket name. So they basically built their graph with these bucket names in S3. So they use S3 as like a giant namespace. That's kind of interesting. But generally speaking, Lambda is not, like I said on one of the slides, it's not like a new concept. It's just a new way to slice and dice what you're already doing. I mean, the logic in your Lambdas are not somehow different than the logic that's in some function in your VM. I think the real difference is economic, is primarily economic, coupled with the fact that it should scale just linearly, right? Every Lambda gets its own memory, its own CPU. So if something suddenly changes and you have 1 billion requests for something, it's not going to slow down, right? So it's not clear to me that at least immediately that there's something terribly new that can be done with Lambda that cannot be done, perhaps slower or more expensively, with your vanilla code. Question was, if you have 2 calls like to the same Lambda, and they're going,
Yes.
they're touching the same persistent object, whatever it is.
No, just a temporary directory.
Oh, /temp. So the /temp is local to each Lambda. So Lambda A /temp is not visible to Lambda B /temp. In fact, /temp is not actually that useful because there's nobody else to pass it to. It might be useful if the Lambda forks a bunch of processes and they want to talk to each other. But other than that, Lambda's, imagine it as a single thread, right? We can already talk to each other in the thread. So one case for /temp might be useful if you're betting on a warm start. You did a bunch of work and you stored it in /temp, and the next time you come along, if you check it, if it's still there, you go, oh great, I just saved myself a bunch of work. But well, /temp is local to the Lambdas. He's next, and then you. You can just yell it out, you're close. So the question is, what are some of the patterns for more complicated applications? I would look to the Erlang ecosystem, because it's very, very similar. And again, I don't think Lambda changes the logic, and you still need to do good software architecture, just like you did before. So it's not clear to me right now that Lambda is going to somehow allow you to do something that you couldn't do before at all. It's going to allow you to do it cheaper, and it's going to allow you to do it perhaps faster or more scalable, for sure. And that's kind of, when you look at Erlang, there are, I forget the name of it, but there's a web server in Erlang, and they quote, nice astronomical numbers up, just like Node. And Node is actually, Node.js, which is a JavaScript framework, is actually very similar to the actor model into Lambdas. They use closures, not actors, but it's the same kind of event-driven thing, right? So the question is the startup time going to be different if it's on the same VM versus a different one? And a warm start's only going to occur if warm start occurs when the container has been saved in memory, wherever it ran last. The container is saved in memory on that VM, which is on a physical server. And another event comes along for that same Lambda, and they light it right there. Once you go, I'm sorry?
It could be a different physical server, which means actually the memory cannot be really.
Well, so the Amazon infrastructure keeps a record of where are the currently dormant Lambdas. So it knows Lambda number 45, there's a dormant Lambda 45 sitting over here. And he's going to be there for the next 3 minutes. And so if an event comes along that's targeted at Lambda 45, I send it there. It doesn't forget where the dormant Lambdas are. It remembers. So if there's a dormant Lambda somewhere, they're going to reuse it. If it's not, then you go cold start, whether you're on the same VM or not. Right? Once they wipe the bits for the container, you got to rebuild the container, reload the Linux, yada yada, whether it's on the same VM or not. So really the whole thing about cloud is to be VM tolerant, right? You don't even when you put an AMI on there, you don't know. You put it on a Tuesday and then you come back on a Wednesday, you don't know if it's you lit it on the same physical server. So it's you won't be able to tell. The same Lambda, multiple copies of the same Lambda can be executing at the same time. So let's say I have an event, whatever it is, someone writes to an S3 bucket, and it always takes me 500 milliseconds to process it. But if the events are coming in more frequently than 500 milliseconds, they come in every 50 milliseconds, I'm going to have 5 of that same Lambda running. No, 10 of that same Lambda running, right? They're going to relight that same Lambda, copies of it, however many times. You can have the same Lambda running in overlapping concurrent fashion, processing the same kind of event. And of course, they're all in different containers, so they don't see each other, right? They don't share any state. And just like any distributed system, the developer has to be concerned about that. If they're all going to write the same object, well, you need to order the writes if you care about that. So remember that the same Lambda can be running a bunch of different times all over the place. Question is, how would you transition from an existing web server? There's a guy behind you and then this guy. How would you transition from an existing web server over to a Lambda implementation? I would do it in pieces. And the nice thing about web servers, and all web servers are like this, they have routes, right? They call them routes, and a route maps to a particular URL with a particular HTTP message. Well, guess what? That's exactly what API Gateway is. So you can actually move it over route at a time and do something interesting and get it working. So web servers are really nice because they're already kind of pre-modularized, by route. If you have something that's not a web server, that's just a bunch of computation you're doing, you can peel, well, again, Lambdas are just functions. You can peel the function out of your existing source base. It's the same source code. The only difference is the interface. Same logic in the interior, right? And do that. Just peel them off 1, 2, 10 at a time, and transition and get your feet wet. And again, you're going to have to learn. There may very well be a part of your system that really wants to be in a VM because it's cheaper. You have to find that out. And then there's some parts that you really want out of the VM because it's going to be cheaper because it's not running anyway, right? So just one other point which I remembered. There are some tricks you can do to keep Lambdas warm. So one is CloudFormation. Yeah, CloudFormation has like a cron feature where every X minutes it can do something. So you can just make it light your Lambda, every 4 minutes. If you really want it to be warm, yeah, it's a ping, right? And he lights up. It's like a health check. And another way to do it is Amazon has something called a T2 Nano instance, which is $5 a month, running full time. It's very weak, but all it has to do is send the packet. So then you can do that. But if you really, really need minimum response time.
Pay for all of this, right?
What's that?
You can pay for all of this.
Yeah, you pay. Well, that's $5 a month for the T2 Nano.
Call.
Oh yeah, you're right. Yeah, you'll 1 10 to the minus 8 cents per activation. But if you really need guaranteed minimum time, you have to use a VM.
You have SLAs.
Yeah, exactly. And you're going to have to partition your system by performance, not just by So the question was, Lambda sounds all good and well, saving money while you're running, but what about the development? And so I think they have more work to do here. I think Microsoft does a better job than Amazon. But they do have develop and run Lambdas locally. They have like an Eclipse plugin, and what's the other one, IntelliJ or whoever it is. And the thing is that if you have a complicated system that's touching a lot of services like SQS, you won't be able to run that locally. But you could probably hit it over the web. They do have a local Dynamo, clone that you can run. But no, that's an area I think that needs more attention. I think Microsoft does a better job at this point. So the question is there basically a marketplace for Lambdas? I don't know if it exists yet, but I know it's coming. Yeah. And I would share graphs of Lambdas too, right? The question was, is there an orchestrator to bring Lambdas, configure Lambdas, getting them running, that kind of thing? CloudFormation, in Amazon's case, they have a service called CloudFormation, and it's basically a bunch of JSON that you can say, what you want. And that will configure your Lambdas for you. You can actually have a template that you can just stamp out and reuse a bunch of different times. And so it works for VMs as well, but it'll do Lambdas. And you can actually, as I said earlier, one of the events that can activate a Lambda is CloudFormation. So you can have a Lambda call to tell it how to create Lambdas. Or anything else for that matter. But so the question is, it looks like, looking at this slide, that Lambda doesn't apply to a very broad part of the solution space. And part of this is due to this. Right? Amazon picked this price. I mean, you can already see they're charging this doesn't count the free tier, but they're charging them 5 times more to run a Lambda per megabyte or gigabyte than they are for VMs. They're already making money on the VMs. So I believe that there's some room here to lower the cost. A lot of this is due to that. So I'm hoping that once Google gets their ducks together, that they'll come in and underprice, and then Microsoft will underprice, because Microsoft's pricing model is identical to Amazon. And I think the way that happened is Amazon was 18 months or more ahead of them, and Microsoft saw, oh look, people like Lambda, they're paying that, so I'm not going to charge less. I'm just going Now there is one difference between Microsoft and Amazon on pricing, is that Amazon charges you the gigabyte number here that they charge you for is the one you configured it for. If you said, I want a 1 gigabyte Lambda, they'd charge you for 1 gig. Microsoft charges you for the average usage over the life of the Lambda. So you'll say, I want 1 gigabyte, that's your maximum. But I think it's every 100 milliseconds they sample, they take an average, and they charge you for that. So that's actually a better model, which means that here, here on Microsoft, it would shift up to the right a little more. Oh, they picked it. I mean, there's. Well, so the person I talked to at Amazon related to me the meeting where he went into the VP and said, hey, I have this idea. Instead of charging every second that you're running, I'm only going to charge, every so often. And the guy says, what are you telling me? We're only going to charge, 30% of the time instead of 100% of the time. So they're taking a risk here in the sense that they're not, with VMs, they're charging you whether you're doing anything or not. They get your money. They're happy. And with Lambdas, they may not be charging you as much, right? There's still a physical server under both of these. They already paid for that physical server. That money's gone. They have to monetize that. So there is a risk to Amazon in doing this. And so I think they're, by doing this thing here, that covers their risk. And I believe this is going to come down. I might be wrong, but I'm pretty sure Google's going to come in under the price, and then Microsoft will follow them down. But again, there's no fundamentally, well, there's something a little more detailed actually, which I wasn't going to go into. But when you look at this, thread here, right? The CPU is going to be burning, the physical server is going to be burning more power during the green than during the gray. If the thread's suspended, it's not doing anything, right? So what Lambda does, it gets rid of the gray. It's all green. And what they're going to try to do is they're going to try to fill in somebody else's Lambdas greens into those empty white spots, right? So they keep the physical server busy, monetized all the time. I think with Lambda, if they really do a good job of scheduling, which they want to do for economic reasons, it's going to increase the total power dissipation of the physical server. It's going to be doing something all the time. It's not going to be sitting there just, I'm waiting around for someone to type So there may be a slightly higher cost to the server, to the cloud vendor. But I think what really was happening here is that Amazon was taking a risk in their revenue generation. So I think they're taking a risk in monetizing this physical server, right? And so I think they were covering that by charging more. So it may be that they're going to make more profit, and then maybe they'll bring the price down. But I don't think there's any fundamental economic reason that this has to be 5x more than an instance, right? The instance is running the exact same code that you could put in a Lambda, right? It's not. So the question is, what is the difference in timing between cold start and warm start? I think it can be seconds. I mean, I haven't measured it, but.
Repeat the question.
Oh, I did. What's the difference in timing between cold start and warm start? So I think the cold start can go up to seconds. I mean, it can be, the worst case is they've got to light a VM and they got to build a container, right? That's the worst. The second level down is, well, they already have a VM, but they don't have your container, so they got to build the container. And then the warmest start is they already have a container, they just put your code in it. So there's different levels of things they have to build that may or may not be there at the time you need it. So, yeah, I mean, I haven't measured it, but I've heard seconds for a worst case cold start. So is the question, can you throttle a Lambda? That's a good question. I don't know if you can. They do have a limit on how many concurrently executing Lambdas are running at the same time. You can set that. But that's not per Lambda, that's for every Lambda, right? If you just want this particular Lambda, I'm not quite sure how often this event's going to happen. I don't want to go crazy. I don't think they have, on a per event. But I might be wrong. I think Kinesis, it might be by service. I think Kinesis might have some kind of parameter, but I don't think all of them do. I think it's interesting, interesting thing to have. There's one over here, and then you. Yeah, it's milliseconds. Yeah. All they got to do is, the best case is your container's there in memory, right? It's probably even less, right? It's just run. So the question is, are people just taking their existing code and wrapping it in Lambda versus decomposing it in a more intelligent way?
Yeah, it's the first part.
Yeah, they should, right? There's nothing stopping you from taking just a whole glob of methods and calling it a Lambda, and you can do that. Again, Lambda is not a fundamental change in modularity. It's still modular, but there is a more optimal and a less optimal way to decompose your system into Lambdas, right? So it's probably the case that a thing that you want to make a Lambda, there's already a method or a function in your existing code. Probably,
Yeah, I'm just
right?
wondering whether people are doing it the right way and decomposing, or just
Well, they should, right? If it were me, I would go and look and go, well, what is my hot path? And what is my most frequent path? Keep that in a VM. Take all these side paths, get them out, and make them Lambdas, right? And I just pay by the use for the low frequency stuff. And then for the high frequency stuff, I keep it in a VM, and it's going to be net cheaper. And the other thing to consider, of course, is the response time. If you really need minimum response time, you got to have a VM. Right? Otherwise, you run the risk of a Lambda cold start, and it's going to affect your response time. So I don't think VMs. With those other ideas that I propose, scheduling the graph and doing things like that, you can certainly start to hide cold starts, and you can also hide. If they do that transparent persistence concept where they preload these objects that you're going to use, they can do that behind the scenes without you having to do it and maybe have your data ready to go. So I think there's a lot of headroom to improve the performance of Lambdas, but it may or may not ever totally kill off the VM. All done? Thanks. Thank you.